Okay, let's do some problem solving now. The problem we want to begin with is a specific heat problem. And the reason why I know this is a specific heat problem is on two levels. The first level is that it states it's a specific heat problem, obviously. But often it doesn't state that title. But I also can know that's a specific heat problem because you'll notice the temperature is changing in this system. There is a certain material that weighs 18 grams, and the temperature underwent a change. Therefore, that heat was devoted to specific heat, was using a specific heat capacity. And so let's take a look at how this problem will be solved. Because it's specific heat, the equation we're going to use is Q equals Cm delta T, where Q is the amount of heat that was transferred during the process. C is the specific heat capacity of the material, the ability to hold heat. M is the mass in grams of the material, and this is the amount of temperature that got changed. Now I'd like to make a comment about this delta T. Delta T is calculated by taking the final temperature of the material minus the initial temperature of the material. And this very much matters. If the final temperature of the material after the heat has been transferred, if that final temperature is greater than the initial temperature, then this overall value is going to be positive. And because the delta T is positive, it's telling you that the heat Q entered the system. The system or material gained the heat, which would make sense because the temperature went up. But notice if I have a final temperature that is lower than the initial temperature, that must mean that the heat Q left the system, making the final temperature lower. And when the final temperature is lower than the initial, then the overall value is a negative value, and that's telling you the heat was removed. And so the sign, positive or negative, very much matters for the delta T. The delta simply means change. So let's take a look now. So in this problem, heat Q is given to you. It's telling you there was 75 joules worth of heat was moved into the system, was absorbed. C is the ability to hold that heat. It's the specific heat. And in this case, that's what's asking us to solve. M is mass of the object, and it's always given in grams. In this case, it's 18 grams. And the delta T, as we just discussed, would be the final temperature, which is 40, minus the initial temperature, which is 15, which gives us a delta T of 25 degrees Celsius. And it's going to be a positive 25 degrees Celsius, and that's very important. It's very informative because we now know that heat moved into the object. So now we plug our values into our equation, and we get 75 joules is equal to the specific heat capacity, which we do not know, the mass, which is 18 grams, times the delta T, which is a positive 25 degrees Celsius. Now when we do the algebra here, we come up with 0.038 joules per grams Celsius. That is C, which is the specific heat. Now what exactly does this mean? What this means is it's going to take 0.038 joules worth of heat energy to change 1 gram of the substance 1 degree Celsius. So that's the units associated with specific heat. Let's take a look at a new problem. This is a specific heat problem number 2. It is more elaborate or more extensive, and in fact it is exactly the problem that you were asked to solve in the lab of specific heat of metals. So let's take a look at it. It says that we have 62 grams of an unknown metal, and we heat that unknown metal to 100. The most common way of doing this is putting it in boiling water. Let it sit there for several minutes, and the temperature of the block becomes the temperature of the water boiling, which is always 100 degrees Celsius. So we transfer this to a calorimeter, which contains 100 milliliters of water at 20 degrees Celsius. And then the water heats up because we place this hot block in it, and it heats up to 25 degrees Celsius. And the question is, so what is the specific heat of the metal? And it's going to ask us to identify that. So let's do a picture of this for right now. What we have is the following. We have a block. So we have a block, very poorly drawn. And this block weighs 62 grams. And we stick it in boiling water for several minutes, and we raise the temperature of the block to 100 degrees Celsius. Now what we're going to do is we're going to put it into what is typically a styrofoam cup. Again, we've discussed this with our lab. And the styrofoam cup is filled with water. Now, when we place the block in that water, the heat is going to exit the block. And upon exiting the block, the heat entered the water, and the temperature of the water went up. And so the temperature goes from 20 degrees Celsius, and it increases to 25 degrees Celsius. And the temperature of the water rises because the heat has entered that system. Now what we're going to do is, ultimately, what we want to do is the following. What we want to do is we want to know the following equation. We want to know that Q of the block is going to equal the specific heat of the block, the mass of the block, and the change in temperature of the block. Now the reason why we want to work with this is you will notice the problem is asking for the specific heat value of the block. So this is what we want. So in order to solve for that, I need to know the total amount of heat that was moved in the block. I need to know the mass of the block. I need to know the change in temperature of the block. Well, we actually know how much the temperature changed by. We know the mass of the block, but we don't know the specific heat. We don't know the amount of heat that was involved. So we have two variables here. So what we're going to do is we're going to solve for the amount of heat that was transferred out of the block by determining the amount of heat that got moved into the water. Because the heat that went into the water is in fact the heat that got moved out of the block. So what we're actually going to start with is we're going to say, right, the amount of heat that was moved into the water is equal to the specific heat of the water, the mass of the water, and how much the temperature changed in the water. So we're actually going to start here. This is the heat that moved into the water. And the amount that went into the water was in fact the amount of heat that came from the block. And so these two values are the same number, and by knowing that, we could then solve for this equation. So let's start here. The amount of heat that moved into the water is going to equal to the specific heat value of the water. Now I'm going to use the calculation in joules. So I'm going to write down the specific heat of water as 4.18 joules per gram degree Celsius. Those are the units. And what that says is it takes 4.18 joules of heat to warm 1 gram of water 1 degree Celsius. We're going to multiply that times the mass of the water. Now it says here that the calorimeter had 100 milliliters of water in it. Well, 100 milliliters of water weighs 100 grams. So I can place 100 grams here. Now, what was the temperature change of the water? The water initially, the temperature initially was 20 degrees Celsius. And the temperature wound up being 25 degrees Celsius. So delta T is always final minus the initial. And so we get 25, which is the final, minus the initial, which is 20. So the delta T, the change in temperature, is final minus the initial. Now when we do the calculation, we find that the amount of heat that entered the water is equal to 2,090 joules. So that's the heat that went into the water. And therefore, 2,090 joules is the amount of heat that left the block. Now, knowing that, I can now use the equation of the block to figure out specific heat. So what I do is I write down, this is going to be a bit of a squeeze here, I write down 2,090 joules is the heat that left the block, is equal to the specific heat of the block, which, by the way, I'm looking for. The mass of the block, it says right here that the block weighed 62 grams. Unfortunately, I have to leave off units because I can't make it fit. But that's 62 grams. Now, the change in temperature, let's think this through. The initial temperature of the block, when you first placed it in the water, was 100 degrees. So the temperature initial was 100. Now, once the heat from the block had moved out completely, the temperature of the water and the temperature of the block was the same. So at the end of this process, the temperature of the block was the temperature of the water at the end, which was 25 degrees. So my initial temperature was 100, and my final temperature was 25. Now notice, the final's 25, the initial is 100. Now that's really significant because 25 minus 100 is a negative 75. If I multiply a negative value through here, it's going to be giving me a negative value. And that's because the heat moved out of the block. The heat was lost. And so when you crunch out the numbers, you get 0.45 joules per grams degrees Celsius. That is the specific heat. The value is negative. Now, what this is saying is 0.45 joules of heat is required to change 1 gram worth of this material 1 degree Celsius. And if you look this up on the standard chart of specific heat capacity, the substance is iron. Because iron has this specific heat capacity. And therefore, those are two examples of how specific heat capacity problems get solved.